So let's ask the question, and this is what we want to figure out. What is the potential difference across an inductor in a circuit? Let's start with the first, more straightforward question. What's the potential difference if the current is constant? You hit pause and try and answer that for yourself. What do you think the answer is? Then when you're sure you think you know what the answer is, come on back and we'll check. So in our ideal inductor, the resistance is 0. That was what we set off with. So we said that R was equal to 0. If we apply Ohm's law, if we say V equals IR, then if our current is constant and our resistance is 0, our potential across the inductor would have to be 0. So if our current is constant, we don't have any potential. Well, we already said that inductors store energy. They must have a potential. Where does that come from? Well, if we apply Faraday's law, we'll get a potential difference when we get a changing flux. How do we get a changing flux? That happens if we change the magnetic field, and that only happens if we change the current. So if we get a changing current, we'll get a changing field, which is going to induce a field and a current, which will give us an induced potential. So that's getting us to thinking that our inductors are going to be able to store energy. They're going to have potential in two cases. So the first case is if a capacitor in a circuit is charging or discharging. We know that leads to changing current. And the second case will be where we have AC circuits where the current flips back and forth in direction. So those are some of the things we're going to be looking at in this inductor section.